Greetings and welcome to Newton's third law post-activity, I should say. Now, you just did this big activity where you did all sorts of collisions between the carts, pulls when you had the hooks, and then even long-range forces with the magnet bumpers. And you were looking for a pattern here in how much force the carts put on one another, both magnitude and direction. And hopefully you saw a pattern there, a pattern that was true whether they were moving at the same speed or different speeds or even moving at all, a pattern that was true whether the masses were the same or even when the masses were different, a pattern that was true for any kind of interaction. And that pattern was the forces exerted were always equal in magnitude and opposite in direction. And that was every single time that you tried it. And so this is Newton's third law of motion, a seemingly simple law in terms of the math. Just says that any time two objects are interacting, the forces are always equal and opposite, the forces that they put on one another. Now, this isn't the kind of pithy way that you've heard Newton's third law of motion probably growing up. The way that it's often said is, for every action, there is an equal and opposite reaction. Now, I don't really like that way of saying it. It's a little nicer way of saying things, but sometimes people confuse what action and reaction mean. The reason why this more traditional statement comes about is it's a more direct translation from the Latin that Newton wrote in. And there really wasn't a word that meant what we mean by force in Latin for Newton to use. So he used these things that could be more completely directly translated as action and reaction. Okay, I prefer to say that it's a Newton's third law kind of pair of forces acting, not an action and reaction pair. And there's a good reason for that, which we'll look at here in just a moment. Okay. Now, again, Newton's third law guarantees that any interaction will always have forces that are equal in magnitude and opposite in direction. There were no examples that we could find that failed, right? No collisions that we could make up. Long range, contact, speed differences, mass differences, angle differences, all sorts of things that we could come up with, and not in one case could we find any difference about this. But again, as I said, even though it's a seemingly simple law, it has some complications with it. And one of the things that people forget about this law is that while it guarantees that the forces are equal and opposite, it says nothing about the effects of those forces, and about what happens because of those forces. And that's what leads a lot of people to think that this law isn't really true. For example, here we have a massive blue cart. It's got some masses on top. And here we have a less massive red cart. Okay? And the red cart's going to stay at rest. And you probably did one just like this. And you saw something happen like this. So the blue cart doesn't really accelerate very much. It keeps going at close to the same rate. But the red cart accelerates a lot and really takes off. Right? And the heavier you make the blue cart, the more the red cart seems to take off. Right? And so you might look at that and say, well, hang on here. If I'm looking at this situation, since the blue cart doesn't really change much, must not be much force, right? Maybe the blue cart's hitting the red cart harder than the red cart's hitting back. However, you did that demo, right? Or you did that in your activity. And what you found, as we found in every single case, is that those forces were always equal and opposite. How can that be? Well, that's because sometimes people forget that there's more than one law of motion from Newton. Right? Newton's second law that we've been learning also in this unit says that the net force is equal to the mass times the acceleration. In other words, the acceleration, the result of the net force, is not only dependent on how big the net force is, but it's also dependent on how much mass you have. As you've seen many times here, acceleration can be written as net force over mass. So if the forces are actually the same size, the reason why the red cart and the blue cart react differently to those equal forces is because their masses are different. Bigger mass, smaller acceleration. So what we're saying here is that, yeah, the forces could actually be equal and opposite, because in the case of the blue cart, we've got this big mass, which results in a small acceleration, equal to a little mass of the red cart times a big acceleration. That's what Newton's second law says here, if we analyze it. So it is possible that the forces exerted on one another are always equal and opposite. Newton's third law just doesn't guarantee that the effects are the same. The effects are governed by Newton's second law, which depends both on how big the forces are and how big the mass is. Other little complications here. Here is a little story, kind of a classic physics story to discuss when talking about Newton's third law. And it's a story about a very smart horse who is trying to get out of work. And so the farmer comes out in the morning and hooks the horse up to the cart, and he wants to go to market. So he hops up into the cart and he says, "Giddy up, horse." The horse turns around. Remember, this is a smart horse. The horse turns around and says to the farmer, "Hey, look, Newton's third law says if I pull on the wagon exerts an equal and opposite force on me." We saw that in our activity, right? We had the two force probes hooked together by the hooks, and if you pulled them apart, no matter how hard you pulled, the other one pulled back with an equal and opposite force. Well, as we've seen in the past, if forces are equal and opposite, they cancel out, and that would mean the net force is zero. And if the net force is zero, then I won't go anywhere. So why should I even bother? Very smart little horse here. So again, he's saying, hey, look, if Newton's third law says that I pull on the wagon's going to pull back on me with an equal and opposite force. Add them up. You add up to zero. No net force, no acceleration. I'm not going to move. Now, obviously, there's something wrong with this, because you know a horse can pull a cart to market. So let's draw a little force diagram here, separate out the horse and the cart. What the horse is saying is, look, I pull forward on the cart. So this is the force of the horse pulling forward on the wagon. Then by Newton's third law, the wagon must pull backwards on the horse with a force which is equal in size and opposite in directions. Same size arrows, right? Just pointing in the opposite direction. Now the horse says these forces should cancel out. But maybe you can see in the force diagram here why they don't actually cancel out. Look at it this way. Of those two forces, how many of them act on the horse? And of those two forces, how many of them act on the cart? Hopefully you see here that there's only one force on the horse and one force on the cart. Yeah, these are a Newton's third law pair, but they don't act on the same object. One of them acts on the horse and one of them acts on the cart. Well, the only way forces cancel out is if they act on the same object. So the farmer can say to the horse, hey, look, yeah, there might be an equal and opposite force pulling back on you, but that's a Newton's third law pair, and they don't cancel because they act on different objects. Only one force acts on the horse and one force acts on the wagon. And so that's a little special thing here about Newton's third law. In fact, if the forces do cancel, they're not a Newton's third law pair. You can think of many examples we've done where, say, the normal force balances out the force of gravity. Well, those actually come from two different reactions, as we're going to talk about shortly. Right? They're not two different interactions. They're acting on the same object and canceling out. They're not a Newton's third law pair. They just happen to be equal in size and opposite in direction because they cancel. So the horse, being a smart horse, says, okay, I'll give you that. But as we see here in the force diagram, if I pull forward on the wagon's going to pull backwards on me. And if the wagon's pulling backwards on me, how am I ever going to go forward to market? Well, again, you know the horse can pull a cart forward. The key to the answer to this question is that the horse and the cart and the wagon are not the only things that are interacting. And think about all the other forces we might draw if we draw a force diagram of the horse. Of course, the first one we always throw on there is a downward force of gravity. This is the earth pulling down on the horse. Well, by Newton's third law, if the earth pulls down on the horse, then what's the horse have to do? It has to pull up on the earth with a force which is equal in size and opposite in direction. Now you might say, whoa, wait a minute here. How is the horse pulling up on the earth? I mean, the earth doesn't rise up. Well, again, remember though, the effects of the forces are not guaranteed by Newton's third law, only the size of the direction. Right? These two forces are one interaction, so they're going to be equal and opposite. But the earth is a huge mass. The little force of gravity here isn't going to really do much that you're going to even notice to the earth. There are, however, interactions between the earth and other objects that are Newton's third law interactions that you can see the effects on the earth. For example, a very near neighbor that's rather large is our moon. The earth puts a force of gravity on the moon, which keeps the moon in its circular orbit, keeps it from flying away. But by Newton's third law, The moon must also put a force on the Earth. You might think, well, oh, wait, what's that? Well, if you've done enough Earth science, you know that we can see the effects of the moon's force on the Earth in the tides. That's why you have high tides when you're turning the side towards the moon. It always has the high tide. Now, these are not the only interactions going on. Right? Also, we might draw a force, a support force from the surface acting on the horse. This, of course, is a normal force. But if the ground is pushing upward on the horse, what else has to be happening? Well, of course, the horse is pushing downward on the ground. And these two forces are equal and opposite. One interaction, Newton's third law. The horse, however, doesn't just, if it's trying to get to market, it's not just going to push straight down on the ground. If you want to move forward, you push down and backwards. So here's the force of the horse pushing backwards on the surface. And by Newton's third law, the surface must push forwards on the horse. So if you see here, there are actually, as far as the horse goes, 4 different interactions going on. The horse interacts with the wagon. The horse interacts with the earth as a whole through the force of gravity. The earth interacts in 2 ways with the surface. One is the force it puts down on the ground, normal force from the ground up on the horse. One it pushes backwards on the surface, and the surface pushes forward. So, farmer can say to the horse, hey, look, if you want to move forward to market, focus on the horse here, we need to have a surface pushing forward harder than the wagon pulls backwards. The red arrow's got to be bigger than the yellow arrow if we want the horse to go forward. Well, how can the horse get the surface to push forward harder than the cart pulls backwards? He can do that if he pushes harder on the ground than he pulls on the cart. Now, this is a little complex here, so you have to slow down a little bit here. Right? If we want this force to be bigger than this one, then the horse has to push back harder on the ground. The harder the horse pushes on the ground, the harder the ground pushes forward on the horse. Likewise, the less the horse pulls on the cart, the less the cart pulls on the horse. So, when these 2 forces, which come from 2 different interactions, aren't balanced, the horse will accelerate. The horse will be able to go forwards to market. And so the horse, having been defeated by good usage of Newton's third law, will pull on the cart, push hard on the ground, and move forward to market. I'll go over another little example of this kind of thing. That's me in my younger years. You can see my tats there. I got my ink and over there. This is actually a picture I stole from the International Tug-of-War competition. Yes, this occurs. There are national tug-of-war teams that pull against one another. But you can see I'm much younger, much less white in my hair and my beard here. Okay, but let's look at what's going on with this tug-of-war guy here. Okay, he's interacting in 2 ways. One is he's interacting with the rope. Okay, he's pulling backwards on the rope. And what's the rope doing by Newton's third law? The rope is pulling forward on him. Now, these 2 forces don't cancel out because one is acting on the rope and one is acting on me. Newton's third law pairs don't cancel because they act on different objects. Well, if this was the only interaction, if I was on roller skates here, I would actually move forward by pulling on the rope. But I'm not doing that. I'm also pushing forward on the ground. Kind of at an angle, but mostly forward at the ground. And so by Newton's third law, the ground must push backwards on me. So if we focus on me here, if I want to win the tug-of-war and move backwards, the force that the ground pushes backwards on me has to be bigger than the force that the rope pulls forward on me. How's that going to happen? I have to push harder on the ground than I pull on the rope. If I can push harder on the ground than I pull on the rope, the ground will push backwards on me harder than the rope pulls forward. There'll be a net backwards force, and I'll accelerate backwards. So it's all about how hard I can push on the ground. I used to sometimes confuse some of the students that would be taking place in the tug-of-war at the assemblies by yelling at them to push harder in order to win. Right? Most people think it's all about the pull, right? But you got to be able to push hard on the ground. I can remember one year when the underclassmen came out to do a tug-of-war with the seniors, and I saw what they were doing to set up, and I leaned over to the teacher sitting next to me and said, oh, look, the underclassmen are going to win. And sure enough, they did. And what did I see that told me that they were going to win? Well, it wasn't that they were bigger. The seniors were bigger guys, bigger girls. They were stronger. They were probably going to be able to pull harder on the rope. But The underclassmen, as they walked out, took their shoes and socks off. And if you've ever been on the gym floor, if you're wearing, and the seniors left theirs on, if you're wearing regular shoes, it gets pretty slick on a gym floor. There's little dust and that are on there. And if you're a basketball player, they always like to clean off the bottom of their shoes so that they can get a better grip. So I knew that the seniors, no matter how hard they tried, couldn't push very hard on the ground before they'd start to slip. The underclassmen, however, if you go on bare feet in one of those floors, it gets kind of almost sticky. So they could push really hard on the floor. And so sure enough, even though the seniors could pull harder, they couldn't push hard enough. In fact, they probably even hurt themselves by sliding themselves forward because they pulled so hard on the rope when they couldn't push very hard on the ground. So Newton's third law here mathematically is very simple, but in application, there's often some complications. We have to remember that Newton's third law forces act on different objects and therefore don't cancel, and that there's often more than one interaction occurring. So we have to keep track of all the interactions and then look at it in terms of net force, mass times acceleration, in order to decide what's going to happen. So I hope you enjoyed this little presentation on Newton's third law of motion.